Hello guys, welcome to Thursday's lesson here. It is April the 23rd. I hope everyone's doing all right. We're going to be moving on with acids and bases today and talking about the pH scale, which you got a bit of an introduction to during your acid-base web quest that you completed last week, which overall you guys did a great job with. So I want to talk about what the pH scale is, what these numbers mean, and what this crazy little calculation is at the bottom of the page that you might have noticed. So if you printed out or copied down the filled in notes, what I'm going to do is take these notes, these blank notes, and fill them in so you can follow along. So that way, if you are taking notes as we go through this, you can keep up. Remember, pause at any time, rewind at any time. But I just want to make sure that everybody understands what's going on here. All right. So with the pH scale, what do we have going on here? So first off, we have pH, and we have to think about what does that stand for. All right. pH stands for potential hydrogen. Now, hydrogen should sound familiar because we've been talking about hydrogen a lot with the Arrhenius theory and also with the Bronsted-Lowry theory. All right, the Arrhenius theory, the hydrogen ion is what was present in an Arrhenius acid. Okay, we looked for that H+. In the Bronsted-Lowry theory, we talked about the hydrogen ion or proton. We referred to it as being donated or accepted, all right, or being given away or picked up by something else. So we're back at this hydrogen. So if you haven't realized yet, you will start to realize very soon that hydrogen ions play a very big part in what is considered to be acidic or basic when you're describing a solution, or what would make, one acid stronger than another acid. Okay? So what you learned in the web quest from the other day, we have this pH scale. It goes from 0 to 14. And this is basically a comparison scale. That's why we say relative strengths. Whenever you see the word relative, it means you're taking the value of one thing and comparing it to something else. So it's, like I said, it's kind of like a rating system, like what's stronger, what's weaker, the numbers getting lower, higher, etc. So we have 0 to 14. 0 would be the strongest acids we could have, and 14 would be the strongest bases. So this number 7, right smack in the middle, would be neutral. Okay, neutral. And the most common neutral substance that we know of is water, H2O. And the reason water is neutral, and we're going to get down to this in a little bit, is because the hydrogen equals the hydroxide concentration. So if you think about what water is made of, you have one hydrogen and you have one hydroxide bonded together. Okay, now think about what we've talked about. Hydrogen ions for Arrhenius acids, hydroxide ions for Arrhenius base. Well, if the H is equal to the OHs, you don't have anything acidic, you don't have anything basic, you got something right smack in the middle, which is going to be a neutral solution. So when we look at this scale, there's something that we do have to realize is that as we go from a lower to higher number on the pH scale, we are actually moving from the acids to the bases. So if the acids have a high concentration of hydrogen ions, as that pH increases, we would say the hydrogen ion concentration, if you remember, concentration are the brackets, decreases. Okay, that hydrogen ion concentration decreases. But in the meantime, the hydroxide concentration increases. Because think about it, we're going towards the bases. The bases have the OH. And then on the other side, we're going to go in the other direction. if I had a whole bunch of solutions whose, all lines up and their pHs are getting lower and lower and lower, well, that tells me that with each of those solutions, that hydrogen ion concentration will be increasing. And the hydroxide concentration will be decreasing. Okay, so that's something we have to think about. When we talk about the highest concentration of hydrogen, and that's going to be the more common question you get with the concentrations of the ions, the highest concentration of hydrogen is going to be down here by 0. So I'm going to put a note. This is not on the filled in notes that I posted, so you might want to add this. When you're at 0, you have the highest concentration of hydrogen ions. And over here, you have the highest hydroxide concentration at the opposite ends. Okay? As one of them, as you can see from these arrows, as one concentration goes up, the other one goes down. Okay? Depending on if you're getting more acidic or basic. So why is water neutral? Okay? Well, think about the formula. You have H2O. H2O is actually a combination of an H plus bonded with an OH negative. So when you see the formula for water, it's also going to be written as HOH. And that's basically hydrogen and hydroxide. Okay, and if you remember from ionic formulas, once you put them together, those charges aren't written in the final formula anymore because they've canceled each other out. So if you have just a glass of pure water, what's going to happen is that water is constantly going to be breaking apart and coming together again. And you're going to have H's and OH's floating around separately, in addition to all the H2O molecules in that water. So this breaking apart, we call the auto ionization of water. And that's when water just automatically breaks up into its ions. Okay? And you can add that to that if you need to. It's when water automatically breaks up into its ions. And it always does this. Water constantly does this. Okay, so now calculating pH. This is something you will not have to calculate, but I'm going to show you a little shortcut, which is great. So calculating the pH is based on the hydrogen concentration, and it's actually a logarithmic equation. You do not need to know this. If you have a scientific calculator, you could plug it in as negative log and plug in the concentration and you would get your pH, no problem. But there's an easier way of doing this. So pH, again, potential hydrogen. You have to be given the hydrogen concentration. And that concentration will be given to you in a notation, a scientific notation of 1 times 10 to the negative something. And there'll be a number there. All right. So the way it works out logarithmically is that whatever that number is, that is going to be your pH. Okay, that will be the pH. Just don't include the negative sign because we don't have that on 0 to 14. All right, so let's say I have a solution that has a hydrogen ion concentration of 1 times 10 to the negative 4th molar. Okay, remember molarity? That was our concentration for solutions, moles per liter. What is the pH? Well, if I have this number right here, if I have 1 times 10 to the negative 4th is my concentration, that is going to be my pH. All right, that will be my pH. Also, don't forget that this number can also be written as okay, 0.0001. So you are going to see these numbers written as in the expanded form as well as scientific notation. So All you have to do is move that decimal to the left if you're, converting it. But in this case, how many times do you move that decimal to get it right after the 1? And that'll give you your answer. So let's take another example. If I gave you, let's see if this is question number 1, question number 2. If the hydrogen concentration equals 1 times 10 to the negative 6th molar, all right, well, what would the pH be? I got 1 times 10 to the negative 6th right here. I'm just going to box off that 6. I am not going to include the negative sign, so the pH would be 6. And then another one, if you were given something in expanded form, let's do this. If my hydrogen ion concentration was 0, oh, that's my dog barking in the background. Let's see. Okay, whoop, molar, there we go. So let's say I have this, decimal points. 1, 2, 3, 4, 5, 6, 7, and then the 1. Okay, so how many places would I have to move that if I were writing this in scientific notation? Well, it would be 1, 2, 3, 4, 5, 6, 7, 8. So that's the same thing as 1 times 10. 1, 2, 3, 4, 5, 6, 7, 8. Good. To the negative 8. I think I might have a different example on the notes. It might be 9, so it would just be an extra 0 if you got that. But that would give us a pH of 8. Okay? So what I want you to realize here is as that exponent gets larger and larger, that negative 6 to a negative 8, the actual concentration is getting smaller and smaller. Because think about it, if that number keeps getting bigger and bigger, I just keep adding more zeros and moving that decimal to the left more. So when we talk about the lower numbers being the strongest acids, well, take a look at this. 0.0001 is a larger number than 0.0000001. Larger number than that, this is larger, therefore this is more acidic because the hydrogen concentration is greater. Okay, so you kind of have to wrap your head around that a little bit, that is the reason why, because of that logarithmic equation, that is why we have lower numbers of pH value being a stronger acid. Okay? So now, moving on, multiples of 10. Okay, the multiples of 10. Every time you change the pH by 1 unit, you are changing the hydrogen concentration by a multiple of 10, because we were talking about that 1 times 10 to the negative 4, 1 times 10 to the negative 6. Those are jumps of 10. Okay, so when the pH is different by 1 unit, hydrogen concentration is 10 times greater or less. So what does that mean here? All right, so I'm going to draw a pH scale here, and I'm just going to use different areas of it. I'm not going to use the whole scale. I'm going to throw 7 right in the middle. I'm going to throw 14 all the way up top, and I'm going to put 0 at the bottom here. All right, let's say that I have a pH of 6 and a pH of 8. Okay, so if I have, let's put pH on the left side, and let's put hydrogen ion concentration on the right side. So if I have a pH of 8, that's 1 times 10 to the negative 8th molar. pH of 7, 1 times 10 to the negative 7th molar. pH of 6, 1 times 10 to the negative 6th molar. Okay, now as I'm writing these out, if these numbers aren't making sense quite yet, please rewind a little bit and go back to the notes where we just talked about that logarithmic equation and how those exponents are matching up to the pH value. Okay, well, as you go from 8 to 7, we just increased the hydrogen concentration by 10. Okay, because look, 10 times -8, 10 times -7. That's one jump with the decimal point. That's a multiple of 10. Now, if I go from 7 to 6, that again is an increase of the hydrogen ion concentration by 10 again. And it's increasing because I'm going from 8 to 7 to 6. I am getting to the most acidic. I'm getting to stronger acid. All right, so we can see that increase in hydrogen concentration as we go from 8 to 7 to 6. Now, let's say I wanted to go from, I had a solution and I added maybe something acidic to it, and it went directly from 8 to 6. Okay, let's say we go from 8 to 6. Well, that would be an increase of the hydrogen concentration by 100 times. Okay, because remember, multiples of 10. So 10 times 10 is going to be 100. All right, so now let's take a look at some other numbers here. Let's start down at the bottom here and just do pH of 1, pH of 2, 3, 4, 5. Just throw numbers. Obviously, this is not to scale. I'm just kind of throwing all the numbers in. So let's say we went from 5. So I'm just going to throw in my hydrogen concentrations. And again, this might be slightly different than the notes, so please feel free to add anything here that you'd like. And I just want to show you the greater jumps here. So let's just say I did a simple jump from 3 to 1. I took something and I made it more acidic, and its pH changed from 3 to 1. Well, you would say that the hydrogen concentration, there was an increase of the H plus concentration by 100 times, or that a pH of 1 has 100 times more hydrogen than the 3. All right, now let's say I went from 4 down to 1. Well, 10 times 10 times 10, that would be an increase of hydrogen ions by 1,000 times. All right, so just remember, multiplying by 10 means you just keep adding a 0. So 10 times 10 times 10, for every jump, your hydrogen ion concentration increases by that multiple. You can also go in a different direction. If I went from, let's say, a pH of 10 to a pH of 12, let's just do the 12 and the 10. All right, let's say that we went from 10 to 12. Well, then we would have a decrease in hydrogen ions by 100 times. Okay, and that's because we are going to a higher pH, so therefore it's getting more basic, and that hydrogen ion concentration is decreasing. Let's see, now our examples. With this, you want to compare, okay? So what we're gonna do here is we're gonna compare the hydrogen ion concentration. All right, we're going to compare those molarities. So if I were to compare something with a pH of 5 versus a pH of 4, we would say that something with a pH of 4 has 10 times more hydrogen ions. Or you could say something with a pH of 5 has 10 times less, or 1/10 the hydrogen concentration. All right, for 7 versus 9, I would say that a pH of 7 has what? Well, it's a jump of 2 units, 7 to 8 to 9. So that's 10 times 10. 7 has 100 times more hydrogen than 9. Actually, I should put that in there. Then pH of 5, then pH of 9, just so we know what we're comparing to here. All right, this, I got 6 versus 10. So 6, 7, 8, 9, 10. That's 4 jumps on the pH scale. So that's 4 multiples of 10. So pH, a solution with a pH of 6, has, here we go, 1, 2, 3, 4. 10,000 times more hydrogen ions than something with a pH of 10. Okay, so this is kind of heavy today in the notes. So we're going to do a little bit of review today with the questions, but we're going to continue on with it tomorrow. Next week we will review a little bit more on Monday. I'll take you through some review questions again, and then probably on Tuesday we'll be having an assessment on this first part of acids and bases, the introduction so far. So we will spend some time on this and going through what you would see on questions dealing with pH.